A blue box.
Oh. Sneaks up on me. All right. Anybody else have questions? Just to remind you, the quiz tomorrow is 6.3 through 6.6. And can we go over 66? Ooh, I like it. A bunch of sixes. So let's see this evil problem. So it's in 6.6, number 66. Let's see. Real 666 is not the actual number. It's 616. But oh well, we can't quite translate things. I don't know if you guys know that. Oh, we talked about this one a little bit, I think. Or no, it was one like this. Let me see. So let's see. So they give you the formula for decibels. I is the intensity of the sound. They give you what I-O is. I not. They give you what that is. I'm looking at the right problem, right? The one about decibels. I'm thinking so. Yes, 66. That's the one. Yes. So I is the intensity of the sound in watts. They give you what I not is. It's 10 to the negative 12. Lowest level of sound that the average person can hear. How many decibels with a sound intensity? So it's really just, it is nothing more than plug that in for I not, plug that in for I, solve for D. And so, it's already solved for D. You just got to plug that stuff in the calculator then, right? Does that make sense? They tell you what I is. They tell you what IO is, I not. Is that all right? No? Yes? No? It's okay if it's no. It's okay if you need more. But tell me something. Okay, you're not talking to me anymore. Fine. Okay, there we go. Thank you. Yeah, so this is not as evil as it sounds. I know it's number 66, late in the further in the homework set, but it actually is not that. It's plug and chug. All right, I like it. Anything else? So let me see. I'm gonna pull this up while you guys are thinking. I really hope nobody did send me a reminder to make solutions for this practice quiz, because I that would be my excuse as to why I didn't. But I guess I still have time to do it. The quiz isn't until tomorrow. So just to show you this, this is the practice quiz, right? So if you go to modules and go down to unit 6, practice quiz 6. There's a bunch of 6s tonight. This is great. And it's a little bit long, but more practice, like I said. So if somebody will right now just email me and say, make the video, Jeff, for practice quiz 6, I could do it, and then you could look at it tomorrow.
I'll do it real quick.
Thank you. Or if you have a question right now about a problem on this, just let me know.
Can you go over number 5C?
Yeah, I love this problem. So I would. I'm sorry. I love all these problems. They're all my babies. Let me ask you this. Let me do a couple things. I'm going to put that up on the board because I want to do some shit. All right. It's a little kind of dark. All right, so the problem is this. What was it in 3 log 4, I think, right? So let me ask you this. What if I had 5 to the log base 5 of 7? Why is that an easy problem? See who remembers.
Don't they cancel?
Yes, good.
They cancel each other out?
So what I was about to say is how are 5 to a power in log base 5 related, they're opposite functions. So of course they'll cancel, and the answer is 7. So what is e to the natural log of w?
W.
Yeah.
W, yes. So these cancel, w survives. Why doesn't that work here?
Because of the 3.
Stupid 3. But of course, what can we do with the 3?
Make it an exponent.
Exactly. Get it the hell out the way. Get out the way. Now these can kill each other. They just want to kill each other because that is log base 10, which is the inverse of 10 to a power. Does that make sense? So you put that 3 up here now. So now that survives, and you get 4 cubed, 64. There's a gimme problem. Yay. All right, I like it. Anything else? Homework, practice quiz.
Can you show the quiz again? I think I have another question.
Oh, sure.
Uh, 6C.
Oh, yeah. So there are a couple problems in the homework that are like that. And they have the exact same idea to start with, which is, I don't know why I'm beating the hell out of this.
We're still looking at the practice quiz.
Oh, shit. Thank you. It's probably better you didn't quite see. I was beating my poor little whiteboard up. So this is easy. How can I simplify that?
Log W x plus, sorry, x times, wait, x times 3?
And 3x is the way we normally
3x, there we
say it.
go, yeah. That
By
one.
the way, real quick, there's a few people that are writing something like log wx. You're writing as log w with a power. That's a totally different. These are totally different things. So the way I would do a log, if I were you, is if it was log base 5 of b, I would put log b and then put a base 5 in. That 5 is supposed to be down. That b is not supposed to be up. That b is not a power. But most of you guys are fine with that. Some of you guys are just putting it in the wrong place. It's going to mess you up later. Now, so that was easy. Why is this one not immediately as easy? Why is this one not as easy as that one immediately?
Because of the
2.
2, and then I do the same thing, get it out the way, and then I can do it. So if there's a coefficient in front of a logarithm, I have no properties for 2 logs plus log or 8 logs plus a third of a log. There's no property for those. There's only properties for log plus log or log minus log. So I have to get those coefficients out the way. And that's where that property comes into play, where it goes back into power. So I can put that back up here, and then I can do 3x squared.
Would you put the 2 on the outside of the parentheses or on the inside?
If it was on the outside of these parentheses, it would be affecting the 3, which there's no reason it should. Does that make sense?
Yeah.
Yeah. Otherwise, that would be a 9. It ain't a 9. Yeah, I like it. Here's another situation. So let me show you 3 things in succession. I say 3 and I forget the third thing. So this, I could bring the 2 out, right? Bam. What about this? What about this guy?
Would it be natural log of x plus like natural log of x?
Nope. So remember, the reason, why does this work? Because this is natural log of x times x, right? And I have a property for log of a product, which is I sum them up, which leads to 2 of these, which led to the shortcut. So that is a shortcut. That is not what, this is natural log of x times natural log of x. There ain't shit I can do with that, right? So that's an immediate thing I want you to realize, is that the only time the power can come down is if it's on the entire argument. What do I mean by argument? It's another way to say input. All right. Hey, my house is back to normal. So what about, God, I'm tired of pink already. God. What about this one? I like this one. Can I take the 2 down?
Yeah.
No, not directly anyway. Is the entire argument being squared? Is the entire input?
Yes. 4 squared by 2. Or 2 squared.
So if you rewrote it, you could do it. That's what you're saying. So this does not equal, so natural log of 4x squared, like this, does not equal 2 ln of 4x. No. But I could rewrite natural log of 4x squared as natural log of 2x, the whole thing squared. And that is 2 ln of 2x. All right, do you guys get the idea? In order for the power to come down, in order for me to use the shortcut, the whole thing inside has to be raised to that power. Not the whole log raised to a power. That doesn't follow. Not part of the input being raised to a power. Nope, that doesn't follow. I can't use the shortcut then. Oh shit. No. Sorry, I got a question in my. No, you're fine. Just put a little note on there when you go to turn it in. All right, I'm answering a private chat question. Does that make sense? It's just gonna, it'll be fine. Okay, I'll accept that. That makes sense, I think. Any other questions, guys? Is that sufficient for that idea? That's a huge idea. That comes back to bite you in the ass later if you're not careful with when that can be applied. Are you guys doing okay out there? I see very few. I see 2 of you. That makes me feel better. If anybody else could turn their camera on, that'd be awesome. That would really help my mental state. There we go. Mental state helped. Okay. Here we go. I got a question. 31 on 6-7. Oh shit. Wait a minute. 31? There's no 30. Wait. Oh, Jeff, what are you doing? This is not a good sign. All right. So this says tumor is injected with 0.5 grams of iodine 125, which has a decay rate of 1.15% per day. I like it. So the amount that I've got is, where'd it go? 0.5 grams. And has the decay rate of 1.15% per day.
What does K rate mean again? Sorry.
So that just means that each day it loses 1.15% of it is, how do I want to say this? 1.15% of the radiation is lost each day.
So negative 1.15?
Yeah.
Oh.
So it's a decay. I like it.
Okay, got it. Thanks.
You're welcome. And they give you the model that you want to use, right? In fact, I think they have, let me see. I want to show you guys. Yeah, this is the one that had Newton's law of cooling in it. Blah, 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 blah. Here we go. Blah, blah, blah. Yeah, they give you, so you've got the example about radiocarbon dating. Yeah, so just so you can go back and kind of refresh yourself as to what the parts of the model are and what they mean. You do have one about decay rate and half-life and all that kind of business. Okay. And I'm just now remembering that this book uses K for that. So I've got since this is a decay, it'll be negative when I go to put it in. So I got my initial amount, let me say that. The initial amount is 0.5 grams. I've got my decay rate per day. So T is going to be in days. And then they ask me, I've forgotten which problem it was, 31. To the nearest day, how long will it take for half? Okay. And do you remember we actually solved for the half-life directly? We have like an expression for the half-life, but you can always kind of rederive it if you want to. So we derived the doubling time, and then we derived the half-life, and I showed you the connection between the two of those. Does that sound at all familiar? And if you want to memorize less, then all you have to do is you start with 0.5 grams. You know K is 0.0115 negative. And you know you want to end up with half of this, right? That's the question. How long would it take for half? Yeah. So then you just solve that for T. Is that all right? So you really just had to go back. Remember the model that this fits into. K is the growth or decay rate. Of course, if it's decay, it makes sense it's going to be negative. That's good, okay. All right, so now we're in chapter 7. Let me see. Let's see, so I got a question 7-1, number 69. Okay, I don't know, that'd be great. Someday I can catch up on sleep. That'd be awesome. 7-1, 69. Ooh, yeah. I like this. So again, this one is in what I have translated for you to mean bonus. So when you see extensions. So this one, a city is located 40 degrees north latitude, assuming the radius of the Earth is 3,960 miles, and the Earth rotates once every 24 hours. Find the linear speed of a person who resides in the city. Oh, that's so yummy. Okay. What do you think that's going to require? Why would it be different? So somebody at the equator would experience a different rotational speed than somebody who's at the North Pole, obviously, right? Or the pole of rotation. Does that make sense by itself? Okay. So if you look, let's see, how can I give you something to work with without telling you just how to do it directly? Well, first off, remind yourself what you need for linear speed, right? So what do you need to figure out linear speed? And then you need to figure out, okay, how do I get that from what they tell me? So the interesting part is going to be, all right, so let me kind of help you out a little bit. The radius of the Earth is 3960 miles, but if I'm at the equator, then that's the radius of the circle I'm sort of sitting on that's rotating, is what we're assuming, right? That's the rotation is around the equator. So I really want you, so if I took a slice through the center of the Earth, let me stop sharing for a minute. If I took a slice through the center of the Earth, there would be this big circle with the radius, and I would be sitting on that circle rotating. So if I am, so I've got this sphere. I wish I had a big ball. All right, so I'm not at the equator. I'm actually at 40 degrees north. So then the slice I'm sitting on is a smaller circle. Okay. I think that's all I'm going to say. That's so evil. But if that's the only problem giving you trouble in that section, you are doing fantastic. And those are a little bit more labor intensive. So when I grade stuff, I kind of give that a little bit more leeway. But I love that problem. I don't want to give too much away. All right. So hopefully that's okay. Well, it's okay, period, because I say so. If you want to ask me more specific stuff, you can always shoot me a question some other way or hang out after class if you've tried some stuff out and you got stuck. Did I miss anything? Anything else from homework stuff that I can? Did I miss one? No, I got that one done. Okay, all right. So it looks like we're caught up with questions. So I want to get back into, I want to kind of review what we've done so far, because it's a very wide-ranging topic, and there are multiple ways that it can be introduced to students. So it seems like every time I teach this, I start somewhere else. Anyway, you don't have to know all the specifics, but everything kind of comes back on itself. So there are multiple places to start and then come back to with trigonometry. All right, so if you have a question, better catch me now, because I'm about to just take off. Here we go. Okay. See anything? Okay. So what have we done so far? Let's take a little step back. We know radians, and these are going to come back very soon. I just don't want to do too much with them at the moment as we talk about other things. Somebody had a really good question, and I talked about this before, but the way that we defined radians was actually related to this, which is where the equation S equals R theta comes from. Oh shit. You guys can tell me, you can't quite see it. Wah! All right, but somebody remind me real quick, what the hell is S? What is S?
Arc length.
Arc length, I love it. So if I'm sitting on the circle, let's say that R is 1 centimeter, and this is 2 centimeters arc length here. How would I figure out the angle? I would just take arc length.
6 divided by 1. Is that 1?
What happens to the units?
They cancel each other out.
And like I told you before, it is completely acceptable to write this, and it's understood to mean radians, because all radian means is part of a radius that this would be. So this would represent 2 radii. That distance would represent 2 radii. It's sort of like saying, well, 10 feet is like 2 Timmys, because Timmy is 5 foot tall. It's like, but Timmy isn't a unit of measurement. It's just sort of a reference thing. Does that make any sense? Because I tried to make the point that when we get to the point where we get the velocity equations and we think the area equations and the, what am I talking about? Well, velocity, yes, because what was, yeah, thinking backwards. What was omega? Do you guys remember what the symbol omega stood for? Little curvy
Angular
W.
velocity.
Yes, angular velocity. So it'd be angle measure per time. And I tried to show you how this equation and this equation were really kind of cool because there's the connection between angular distance, angular velocity, and linear distance, linear velocity. It's that multiplication by radius that brings me back. So this, the reason, so if I knew, let me see, how can I? So the example I gave you last time is if I know that the arc length was 3 radians per second, and I knew the radius is 2 feet, then the linear velocity would be 2 feet times 3 radians per second. That looks really weird, foot rad per second, but I told you this guy just gets out the way. 6 seconds. Okay. And it is because this really does mean 2 radii. So then what would the linear distance be? Well, when I multiply it by how long a radius is, it's kind of like I'm taking into account how, what a radius is. I don't know how else to say that. So the radians are not really a unit that's there. They just get out the way for the real units. And you can see it right there, the real units cancel. Okay. I didn't mean for that to take that long. I meant that to be a little side trip. All right, let me take this away. That away. So that was a collection of sort of like a little thing in itself, this little trip we took through these equations and through these ideas. Then we focused on trig stuff. Trigonometric functions. And this was the part that there's a ton of ways that it can be taught. And I think I've tried every way so far. And I like each one of them. They all have their own bonuses. So the way I decided to do it this time was to completely start with triangles, because you don't actually have to do that. Let's call these what they are. And the book will go between R and H on this, I think possibly, or some books will. So let's remember what we know so far. So if this is A, what would sine of A equal? What would that be?
Y over R.
Yeah, Y over R. So I tried to get this through to you guys, and I don't know if it really got completely through. This function didn't ever really need to exist. But once we created it, we used the hell out of it, and now I'm like, I can't even imagine it not existing. So all this function is that whole discussion I had about, I don't care how big this triangle is or how small the triangle is, the ratios of sides will always be the same for a given angle. And I think everybody pretty much got that. Because for any given angle, the triangle, if I blow it up or shrink it down, all the sides grow or shrink by the same multiple. So of course the ratios stay the same. So that sounds like a input-output connection. So it kind of made sense to make this into a function. For a given angle, we'll call the ratio of this side to that side, we'll call it sine. And of course, cosine is what?
X over R.
X to R, I like it. And then of course, tangent,
Y over X.
y over X. Kick ass. Kick ass. I like it. All right, and then we sort of played around with these. We discovered for certain values, we could actually figure out what the values were specifically for just a few. We are not going to memorize down to the point where I'm going to know what sine of 11.2 degrees is. It is something, but there are certain values that we know the values for. So for example, somebody tell me what sine of 30 degrees is. Ooh, you're working now, dude. I don't know if you guys remember the thing I showed you to try to make this easier to remember. There's even another way. Let me.
1/2.
Yes. Do you guys? So let me ask you this: what are the possible things for sine and cosine? 1/2, rad 3 over 2, rad 2 over 2, 0 and 1. Is that cool? You guys get that idea? So for all the angles that you're going to be responsible to know, those are the possible values. So if you look back over what we did with 60 degrees, 45 degrees, 30 degrees, that's it. Those were all the values. So here's what I do. All right, stay with me. This is why I don't like, this is one reason why I don't like SOHCAHTOA. Here's what I do. I don't have any of this shit memorized. I don't. I remember that this sine likes y. So it's going to get bigger the closer the angle gets to the y-axis. So if I'm close to the y-axis, sine is going to be big. If I'm far from the y-axis, sine is going to be small. So 30 is far away from the y-axis. It's going to be the smaller value. It's going to be 1/2. So I don't know if that makes sense. You don't have to memorize these the same way I do. I'm just giving you an option. You could just straight up memorize all of them. I don't know why you would want to do that. I really don't. But you can. You can just memorize them straight up. So if I have to think of something like, what is cosine of 30? Well, it is close to what it likes. Cosine likes x. 30 is close to the x-axis. It should be the bigger value, rad 3 over 2. So these two are the extremes. These are for if they're on an axis. This one is when they are equal to each other. And at what angle are they equal to each other? At what angle does sine and cosine equal each other?
45.
45 degrees. Love it. So the sine of 45 equals the cosine of 45 equals rad 2 over 2. I like it. Is that me? Is my phone going? All right. So that's an issue. That is something you want to get on top of right now. Because the quickest way to make me cry or any calculus teacher cry is if you don't know what the shit cosine of 60 degrees is. If you can't think about it for like 10 seconds and tell me, that makes us cry. It makes me sad. Gotta know what those are. Okay. And I am not a fan of just straight up memorization without any connection to concept. That's why I try to give you ways to remember it based on the ideas behind it. So let's do this. Let's do what should be not an evil problem. Let's see if it is. So see, that's angle B. Let's say this is, what you got, Jeff? I think 724.25, is that right? Somebody check me. Do you know how to check that? Is that a right triplet? Is that a correct Is that a valid right triangle?
No.
Uh-oh. All right. So that's me and my bad memory. Yeah, yum it, Jim. Let me see. No, it is. All right. Let's all make sure we know how to check it. What's got to be true? If this is a valid right triangle, what must be true? What can I write? What must be true about the sides?
A squared plus B squared equals C squared.
So you would check this. And this is true. So this is a valid right triangle. You guys understand? So I couldn't just put 5, 7, 11 and just start doing shit because that's not a valid right triangle. Okay. Let me stop for a minute. I don't want to go too fast, but at the same time, I want you to realize you know the basics behind a lot of this stuff. It kind of, some of this is repackaging stuff you already know. Some of this is brand new, possibly. Right, these symbols. But like any function, I just have to know what that really means. It means the ratio of those sides. All right. So can you take a second or several seconds and tell me what the sine of B is, cosine B, and the tangent B?
7/24.
Wait, no, I didn't mean tell me. Sorry, buddy.
Whoops.
That's all right. Just take a few seconds, write those down. Okay, so somebody tell me what sine of B is.
Seven over 24.
No.
7/25.
Yes. Y to hypotenuse, right? Y to radius. You guys, is that cool? You guys see that? And then cosine is going to be the other side.
24 over 25.
So the only trig functions that don't have this in it are going to be the tangent related functions. So what's the tangent going to be?
This one's 7 over 24.
Yeah, 7 over 24. So tangent is y over x, or it's also sine over cosine. They both mean the same thing. All right. So let me throw this one at you. Let me see what you think about this guy here. Given, given that tangent of theta is, what are you doing? What do you got? You got 3/7. Find sine theta and cosine. And let me give you one more piece of information. It's in quadrant 1. That will become an important thing later. I'm not really focusing on the negative stuff yet. So here's what you can do. If I have the triangle, I can write the ratios. If I have the ratio, can't I create the triangle? What do I know about this triangle, given what I know about tangent?
Y equals 3.
Y is 3.
X is 4.
No?
Sorry, X is 7. I thought that I just can't read.
No, I can't write either. It's a bad combination. And of course, to figure out sine and cosine, like we just discussed, what's the one side they both need?
The hypotenuse.
Hypotenuse. Cool. So finish that out. Take a few minutes or like 1 minute. Figure out what sine and cosine are.
Is it 58?
Huh?
58?
No, no, definitely not.
Wait.
The
Square
square
root
root
of
of
58.
58.
Yes. There you
Oh,
go.
square root. Sorry.
I like it when people are like, "I was close." No, but yeah, you got the right first step. Don't forget to square root that bad boy. So now it's not too bad. What would the sign be?
3 over the square root of 58.
Yep. So what would it be then?
Three times the square root of 58 over 58.
Kick ass. Kick ass. All right, gotta rationalize those bad boys. And then cosine theta is going to be
7 times the square root of 58 over 58.
yeah, like 7 over square root of 58, which is 7 rad 58 over 58. Is anybody not cool with going from here to here? Are you guys decent with what happened here? You really want to make that just an automatic thing that you do.
So the 3 comes from given the tangent, right?
Yeah, in fact, the minute I drew the triangle, I could forget about this guy. So he helped me set up the triangle, and then I can answer these looking at the ratios of the sides of the triangle.
Okay, I get that.
I like it. Coolness, I like it. I like it. Okay, okay. Let me think. Let's try. Yeah, let's go ahead and sneak into the negative stuff right now, and then I'll do. Yeah, all right. I'm trying to figure out the order that I want to do stuff in. So if I was in quadrant 2, right? So I am over here. What is true in quadrant 2? My x's are what, and my y's are what? Positive and negative.
X is negative.
X is
Y
negative,
is-
Y is positive.
Y is positive.
Right. So let me ask you this then. In quadrant 2, which trig function or functions are positive? Which are negative?
Is sine positive? Or
Sine is
sine, yeah, and then cosine is negative.
I love it. And cosine is definitely negative because cosine goes like x, sine goes like y. There's multiple examples of where SOHCAHTOA sucks and sine likes y, cosine likes x, kicks ass. I'm not saying SOHCAHTOA doesn't help in one situation. But anyway, sorry, I'll stop. And what about tangent? Which one is it going to be?
Negative because
Got to be negative because it's the ratio of these two. So tangent will also be negative. Now I'm not. Please, dear God, don't memorize this shit, right? Please don't memorize this. Why would you? You could just go based on the problem. So if I told you that I have an angle in quadrant 2, right? Meaning it goes from 90 to 180 degrees, or pi over 2 to pi radians. And I tell you that sine theta is, what do you got, Jeff? 4/9. Why not? Can you figure out what cosine and tangent will be? just to make sure everybody's on the right track. What goes here?
4.
Where does 9 go?
Bottom.
Mm,
It's the hypotenuse, so it's the longer
Oh,
side.
yes, hypotenuse, sorry.
that's right. I got it.
Would it be the square root of 65?
Yeah, so 81 minus 16, 65 squared is 65. And there's 2 ways to handle this kind of problem. You can either make this negative right now. Do you see how I sort of put my triangle facing that way? So it's in that, and see how this is the negative? Or you can just know this shit and put a negative on these 2 and then figure out the ratio. Either way is fine. This way is a little weird, isn't it? Because you're not used to seeing like a triangle with a negative side length, but we know better. We know that's not what that's saying. We know that just means it's in the second quadrant. So of course this piece is negative. That's the negative part of the real axis. The real numbers line. Or if you don't like that, you can just do what I do and just put a negative when it's the right time to put a negative. So then what's cosine going to be?
Square root of 65 over 9.
And what's tangent going to be?
4 times the square root of 65 over 65.
All right, I like it. So it is a logical extension to do exactly what we just did. If I was in quadrant 3, that means that x and y are negative. So in quadrant 3, sine and cosine will both be negative. And tangent will, of course, be
Positive.
because it's a ratio of sine to cosine. And then you can figure out quadrant 4. It'll be the reverse situation there. Quadrant 1 is the easy one. Everything's freaking positive, right? Okay. So next thing I want to do, let me see what time I got. Good. I got enough time. Make sure I don't miss anything. Yeah, we sort of did. Yeah, I'm not really going in perfect order with the book, and I probably never would when I'm talking about trig functions. Yeah, I do want to do that. Let's do this right now. All right. No, all right. I just decided to do it in a different order. I'm going to erase all this business. So let's go back to this kind of problem. What if I was flying a kite? Yeah, okay, this is fun. This is, and I let out, I know I let out, let's say, 22 feet of kite string, right? And I know this angle, because I got this cool little device on my kite string. For some reason, I paid like too much money for this kite. It's got an angle measurement there. And I know that this angle is, do it, Jeff, what is it? 56 degrees. So now I'm curious, how freaking high up in the air? High? Yeah, how high up in the air is my kite? I have little kites up there. All right. Can you see which trig function would allow me to set up the ratio based on what I know and what I don't?
Would it be tangent?
No, because tangent requires me to know the y piece and the x piece. And I don't know the x piece. I do know the y piece and the hypotenuse, right? The r
Sine.
or the sine. Okay, I love it. No, let's just stop right there. That's the thought process to do this kind of problem. And this kind of problem is one of the bedrock problems of trigonometry. It is the immediate usefulness of trigonometry. I didn't say the only, I said the immediate. And then there's like a never-ending avalanche of other uses for it. But this is like immediately the usefulness of it. So I have to pick which trig function. I don't know this side, and I could never know this side right at the beginning. I can't. I get right in terms of h, but why would I want to do that shit? So I'm going to use sine. Sine of 56 equals what ratio do I set up?
H over 22.
H over 22. I love it. And how do I solve for h?
Multiply by
Multiply.
22.
Multiply by 22. So it's going to be 22 times sine of 56 degrees. Now, you're going to see a lot of problems that are this, and then they make this a little more complicated, but they really just come down to which trig function relates what I want to know with what I know. In this case, sine. Now let's talk about how the hell to put this in the calculator. And while this is in my head for some reason, I'm sorry. Again, if you chat at me when I'm up at the board, I don't look at it. Did you get it right? Yes, good. Did I ever tell you guys about Desmos? Did I tell you about that website? Okay. I feel really bad. I noticed people are using it in the homework, which kicks ass. Desmos, let me pull it up here so I can show you real quick. Sorry, I just want to do this while it's in my brain because I've thought about talking about this for weeks and I just forget the minute I'm teaching. So let me show you this. So if you go to desmos.com, this is what it looks like. And I can plug in here y equals 3x squared minus 4x minus 5. And then look at what it already knows to calculate. Can you guys see that already? Let me pull out a little bit. Look right there. It knows to calculate the vertex. It knows to calculate the intercepts. Right? Isn't that nice? And you can kind of zoom out, you can zoom in, it kicks ass. So I'm really sorry that it's such a beautiful tool, and I should have told you a lot sooner. And as long as I've got is it Ninja Plot or is it Plot? Oh, it's Plot Ninja. One of my students from a few semesters ago actually created this. This is not going to help us in this semester, but in case you have to take Calc 3, this is a 3-dimensional graphing tool. And this is just way too cool. Are you kidding me? Sorry, it's not going to help us at this semester. I'm so sorry, but just want to show it to you guys while I was thinking about it. All right, let me pull up my calculator so that we can try to plug this into it. And I will tell you a sad story from my past. Oh, well, you know, it's just like anything on the internet. You go into it with your own risk. Okay. So I am going to put that into the calculator, but I want to show you what to be careful about. The calculator has to be set in the correct mode. Do you guys notice a word at the top of my screen that relates to what we're talking about right now?
Isn't it mode?
Yeah, but look here, right here, normal, float, auto, real, radians. Oh shit. And of course, this problem is currently using degrees. So if you're in the wrong mode, if you stay in radian mode and I put this in my calculator, it's going to think that 56 is radians. So you're right, whoever said that, I'm sorry. Mode is how you control that. So right there, it's either radians or degrees. So if I select degrees, now I can safely, and I can see right there, 22 times, what was it? Sine of 56. Here's your sine button, sine, cosine, tangent. Bam. All right, so it's 18, what was it? Feet, 18 feet up in the air. Roughly. So right in the middle of your calculator are the sine, cosine, and tangent buttons. And of course, above that are what we will eventually talk about, the inverse trig functions. Yeah. Okay, so just to show you, if I was in the wrong mode, let's see what this says. Very often it gives me something that does not make any sense. There we go. So if you used radians, you would be 11.5 feet underground. Your flag would. I'm like, what the hell kind of flag is this? It's got some kind of tunneling thing on it. I don't know. All right. Okay. So now we can, so there are certain angles you have to memorize, and then there's certain angles that you just throw the old calculator, because we can't, no way we're going to memorize all of them. That's insane. I think the last thing I want to talk about maybe is there's a total of 6 trig functions, and we've talked about 3. And there's actually other functions that are related to trig functions, but there's 6 basic trig functions. So we have sine, cosine, tangent. And then, now this seems kind of silly, maybe, I don't know. But we have defined their reciprocal functions. So in the book, you're going to see reference to the reciprocal functions. So and this is really interesting. So there's something called the cosecant cosecant of an angle is 1 over the sine of the angle. So that would be r over y. But do you notice the problem we did earlier, where we discovered the sine, cosine, tangent of a given angle, of a given triangle? It's like there's not that much work. I figure those 3 out, and then I just turn them over, bam, 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 and I got the other 3. So this isn't that huge of a deal, not yet. When we start graphing this stuff, that's where it's going to get funky. The inverse of the cosine is the secant. So that's 1 over cosine. So that's x over, yeah, x over r over x. Cosine on the brain. So what I kind of like about this is s goes to c, c goes to s. Again, that's the way I have it in my brain. I don't know if it's going to work in your brain, but something has to work. And this seems really strange. And there are deeper reasons for the names of these. You'll notice that that's secant, that's cosecant, that's sine, that's cosine, that's tangent. So you could probably guess what that's got to be. What's the only one of the pair that's missing?
Cotangent?
Yeah, cotangent. This would be cotangent. So you might notice that the reasoning behind why we call them what we do isn't immediately obvious. Like, why is that cosine and why is that one cosecant when that one is the reciprocal of that one? So we still have a little bit to get through to come back and really see why it makes sense we call these what we do. But that's what these suckers are called. Okay, I like it. So, you know, if the tangent of some angle, tangent of beta is 4/7, then what's the cotangent of beta?
7/4.
7/4.
Great. That's crazy. All right, and so forth. So that's why it doesn't really change what we did earlier. We find these three and we reciprocate, reciprocate, reciprocate. Now we got all six. It's amazing. Like it. Okay, I like it. Let's see. That's one.
So in what real world situation would you use a one of those, the cosecant, secant, or cotangent? The reciprocal. There you go.
To be really honest, most of the time, if I solve some model and I have 1 over cosine alpha, writing it as secant alpha just makes it look better. That is not the whole story though. But I mean, on one level, that is actually pretty true. That's, oh, we just decided to define these. This isn't really the history of it, but you can look at it as if we just wanted to give 1 over cosine a cleaner representation. There's more to the story than that, because these, all right, let me show you this. I wasn't sure when to kind of start talking about this, but I might as well show you this because that's a very good question. And that's part of the problem of trigonometry is you got to lay the groundwork, and some of the groundwork is built on things you have to learn later once you understand the basics better. And the naming convention is one of those things, but I can show you this. I think it's going to be safe. Let me see if I still have it somewhere. Yeah, there it is. Where was it? No, not you. This one. Yeah, I was trying to find a decent one. The one I used to always go to was taken down. This will work. Let's see what you guys think about this. There's better ones somewhere, but oh well, too bad. Where'd you guys go? There you go. All right, so this. So I want you to pay attention to what makes sense. Watch the cosine. Just watch. Don't worry about any other shit. Isn't the cosine making sense? That's the x piece of the triangle. And of course, it grows as it gets closer to the x-axis, and then it's 1, and then it shrinks as it goes away from the axis, and then it's 0, and then it's negative. And then as you watch the sine is the y piece. So cosine is the x piece in a unit circle. Sine is the y piece in a unit circle. And then tangent is this very interesting, look at this. Tangent is this guy. And think about this. When is cosine 0? When is the cosine 0? At what angle? Since cosine likes x, it's going to be 0 where there's no x. And I don't know if you guys even really get what I'm saying.
Is it 90?
Say it.
Is it at 90 degrees?
90 degrees. Okay, beautiful, right? Isn't 90 all y-axis? That's what 90 degrees is. It's all y-axis. So the cosine is not going to like it there. It's 0. It's like, this is shit. Nothing here for me. Sine is happy as hell. Sine likes y. Sine is 1. Sine is happy. So at 90 degrees, if tangent is sine divided by cosine, and cosine is 0, what does tangent approach as the angle approaches 90? You can see it happening over here. If the bottom goes to 0, the whole thing approaches. I don't know what's happening. Tangent is sine over cosine, sine theta over cosine theta. So at 90 degrees, cosine is 0. What happens when the bottom goes to 0?
Isn't that undefined? It's an error type of thing.
We know better than that now. The limit as the angle, I'm sorry, don't say the limit. As the angle goes to 90, the output goes to
infinity.
Infinity. So watch this line right here. Do you see how it's, as it moves, it's going to identify how tall that green line is. That green line is tangent. And the minute it's straight up and down, it's infinitely tall over there, because if only I could stop this stupid thing. Why can't I stop you? Oh, well, at least I made you less crap around you. I really want this to make sense. If it's got a little bit of an angle to it, it will eventually move over and intersect this green line, won't it? And that would be the height of the tangent. But as it gets closer to 90, right when it's at 90, it's never going to go over there. So when does it intersect that green line? At infinity, which is basically saying never. So this is a visualization. This is another way to consider what tangent is as an actual physical measurement of a part of this unit circle. Sine and cosine sort of live inside, don't they? Tangent lives outside. Now notice, I wish you could see this better. I've got to find a better, see, there's cosecant and secant, but you really can't see them that well. I know, I'm sorry. I'm going to find a better animation. I used to have one of these that I went to and it's gone. That website's gone. And then I find images that aren't as good as an animation. So I'm going to find something. But you can see cosecant inside. You can see cotangent actually over there. Let me see if you can see it. It's really faint, unfortunately. There's cotangent right there. But anyway, I'll stop. So that is another valid way to consider what these are, in which case all 6 of these have their own definition in that animation, in that image. So they're all their own thing. So in one sense, their own thing that happens to have these connections with each other. So that's kind of nifty. All right, I really wish
I like
was in
it.
class.
It actually helped me visualize it and understand how each one
Yeah,
kind of relates to each other.
I'll find a better animation. I have to find a better. I just started looking for it today just in case I wanted to show it tonight. And I was like, this is the best I could find. So I'll try to find a better one because it's so beautiful to watch the secant and stuff doing their thing too. All right. So what we still have to cover, we've touched on things from 7.1 through 7.3, and I think 7.4 also, because their chapter 7 is kind of repetitive. It goes back and pretends like it didn't talk about something it already talked about. But oh well, it's a free book. What do you want from me? So I think we'll finish up chapter 7, or at least firm up everything we've done so far in chapter 7 tomorrow. What's up? Is everybody all right? Any questions?
What's the quiz on again?
6.3 through 6.6.
Got it. And it's tomorrow, but it's due Friday, correct?
That's right.
Okay, perfect. Got it. Thank
That's
you.
awesome. Because then I can actually grade them over the weekend. Yay. All right. So I'm going to call it. This is the end of class. Let me know if you want to hang out afterwards, if you have any questions. Otherwise, I will.
Thank you. Have a good day.
Dude.
Thank
I
you.
miss being able to see people's reactions. You're welcome. All right, guys. I'm out.